Hey, what's up? It's your old pal, Mr. Cook. Let's go ahead and work through this next couple problems, number 9 and number 10. Yeah, we'll do 9 and 10. Okay, so number 9. This function has a removable discontinuity. Assign a value to f of x that removes the discontinuity. Assign a value to f of x that removes the discontinuity. Yeah, that's a head scratcher. I don't quite know what that means. Assign a value to f of x that removes the discontinuity. Well, I think I know what this is. Maybe this is getting. I mean, I don't know. I'll try to cover all the bases. So first off, let's figure out where the discontinuity happens, and that's obviously going to be right over here, because x should not be allowed to be equal to 5. Because if I did, that'd be a division by 0. So that's the first thing that I kind of instinctively kind of guess is that maybe this question is asking where the discontinuity happens, and that in that case x is not allowed to be equal to 5. The other thing that I would guess is that this is asking me to factor it and then remove the discontinuity. So I'd try that as well. So f of x, I'd use that difference of cubes expression again, where it looks like this: a to the third minus b to the third. Remember that factoring that we did in the previous page? It equals a minus b times parentheses a squared plus ab plus b squared. And in this case, a would be equal to x, and then b would be equal to 5. And then I'd go ahead and plug those values in. So the top part is going to factor to become x minus 5, and then x squared plus 5x, and then plus 25, because that's 5 squared. And then that's all over the x minus 5. And the x minus 5s cancel each other out. So that means that this function would be equivalent to x squared plus 5x plus 25. I think that's actually what they're asking us to do. Assign a value to f of x. So reduce it, I think, after you remove the discontinuity. So I'd remove the discontinuity. So I think that maybe it's asking for that as well. So that's what I would assign as equivalent to f of x without the discontinuity in it. Okay, next up, number 10, sketch the graph that satisfies the given conditions. So it looks like I've got some coordinates here, and then I've got some limits for the rest of it. So let's see how we would graph this out. So the coordinates first. When x is -3, y is 1. So go over to -3 and up 1. There's one of my points that I need to graph. The graph needs to pass through there. Another one is 1, 0. So when I go over to 1, 0 is one of the values. So I have a 0 right there. F of 4 is equal to 1. So that means when x is 4, y is going to be equal to 1. So there's another point right there. And that's it. So those are all coordinates. Then we got some limits. Let's see what's going on here. So for this one, it looks like x is getting really big. When x is getting really big, when it's going to infinity or negative infinity, this is where we have end behavior. So it's what happens at the graph on its extremes, like on the left-hand side and the right-hand side. This will tell me what's happening with the graph as x goes to the left, okay, because it goes to negative infinity. And what it's saying is that the graph is going to be essentially y equals 2 on the left-hand side. So if I, graph y equals 2, it's like a horizontal line. So what this is basically telling me is that this is a horizontal asymptote, okay? So as x gets really, really big and negative, it's going to be, about that line. And I think that it's actually going to go like this. It's going to probably pass through this point right here and then follow along this line forever, okay? And what this says is as x goes to positive infinity, so as it goes to the right. So as it goes to the right, it's going to turn into y equals -1. So if I draw a line through y equals -1, it's like this. And that tells me that as x gets really, really big, it's basically going to go through that. So I don't know what the rest of the graph looks like, but it's probably going to go towards that, that line after 4, perhaps. That could be one version of how the graph looks. But those are definitely horizontal asymptotes, both of them. Okay, the next ones. So this one is centered around -1 on the left and the right-hand side, and they're both going in opposite directions. One's going to negative infinity, so going straight down, and then the other one's going to positive infinity for y, so straight up. And so when that happens on the left and the right-hand side of some value, that's what we call vertical asymptote. So there's going to be a vertical asymptote at x equals -1. So if I go to -1, I draw a vertical line like this. So there's my vertical line. All right, so it looks like from the left-hand side of -1, it's going to go to -infinity. So as the graph keeps getting closer and closer to -1, it's going to go straight down to -infinity like that. And I'm pretty confident that's how it's going to look. And then on the right-hand side, it's going to go over to +infinity. So it's going to go straight up. So from like maybe this point right here, it's going to go straight up along the vertical asymptote like that. So that's another piece of my graph that I've got. Oh, and then the next one, it's the same kind of thing. It looks like it's centered around 3. So on the left-hand side, it's going to -infinity. And then on the right-hand side of 3, it's going to +infinity. So it looks like this on the left-hand side, and then this on the right-hand side. So that means that, again, at 3, we've got a vertical asymptote. So 3 is going to have a vertical asymptote right here. There we go. And then on the left-hand side, it's going to go to -infinity. So straight down. So it's just going to go straight down like this forever, okay? And then on the right-hand side, it's going to go to +infinity. So it's going to go straight up instead. So it's going to go straight up along the vertical asymptote forever like that. So that's a version of what the graph can look like. Maybe not necessarily exactly like that, though. Okay, yeah, maybe I'll do this one, number 11 as well. So it says to use the intermediate value theorem to show that the polynomial function has a 0 in the given interval. Okay, so I'm going to use the intermediate value theorem. And what that means, to use the intermediate value theorem, I need to show the 3 things basically are true. Okay, so 2 conditions. One condition is that the graph needs to be continuous over the interval. I need to show that. And it needs to be continuous over the closed interval of the x values, okay? Next, I also need to show another thing, and that's like that at the endpoints. So let me change this to just an a and a b instead. So over those 2 endpoints, if I plug the function in for a, and I plug the function in and use b, that these values are not the same, okay? They're different in some way. So what the intermediate value theorem states after I show these 2 conditions is that they're like by the intermediate value theorem, it says that if those 2 numbers are different, f of a and f of b, then that means that for some value f of c that is between those 2 numbers, f of a and f of b, in some way, it's like either less than or greater than, it doesn't really matter, like whichever one of the 2 it's greater than. If it's between those, then that means that that for any f of c that's between those 2, and maybe I should show an inequality for that. No. I'll just use numbers. I'll use numbers to use it. Yeah. But basically, like there needs to be some value c that's in this interval that gives me a number in between those 2. Okay. And I'll show you what I'm talking about in a second. All right. Let's use the intermediate value theorem. So the very first condition that we need to make sure is true is that it's continuous over the interval. So with this graph right here, there are actually no places where it's not continuous. It's a polynomial. Can you think of any x values that are not allowed to be plugged in there? I can't. So that means that here's what I'd say. So for my first condition to show it's continuous, I'd say f is continuous over the interval from 1 to 2. And that's a true statement. It's continuous. So I don't need to prove anything. I just need to make it a declaration. That is true. Show the condition is met. Number 2, I need to show that f of a is not equal to f of b. So for this, I need to show some work. So here's my a value and here's my b value. I'm going to plug them in. So f of a is f of 1. And let's see what happens when I plug that into this function over here. I get 2 times 1 to the 3rd minus 3. So that's 2 minus 3, which is -1. And then I need to get the other one. So f of 2 now. So I'm going to plug in 2. 2 times 2 to the 3rd minus 3. So 2 to the 3rd is 8. 8 times 2 is 16. So 16 minus 3 is 13. Okay, so I've got those 2 numbers, and sure enough, the second condition is true. F of 1 is not equal to f of 2. So what the intermediate value theorem guarantees is that for every single y value that's in between these 2 values right here, -1 and also 13, that there has to be some number, c, that's in this interval that gives me that. So in other words, f of c is going to be equal to any number that's between -1 and also 13. And guess what? 0 for sure is in between -1 and 13. So that means that there has to be some value c that works with that by the intermediate value theorem. So once I show these conditions, these are non-negotiable. You need to show the conditions. Now I can use the intermediate value theorem. So here's what I'd write. I'd write out a little sentence. by the intermediate value theorem, there exists a C in between these two numbers, 1 and 2. And I think that this one needs to be an open interval, actually, 1 and 2, such that f of C is equal to 0. And the reason why 0 has to be in play is because 0 is in between -1 and also 13. And I can write that off to the side if I want to. -1 is less than or equal to 0, which is less than or equal to 13. That'll work out as well. All right, there we go. That's using the intermediate value theorem. Now let's call this one. That's the end of this video, and let's go to the last one and do that last problem, number 12. See you then.